This video is designed to accompany the organizer from Unit 9, the kinetics unit, on potential energy diagrams. So make sure you take out that organizer as you watch this video, because you're going to be drawing some lines on these graphs so that you can learn the material. All right, so potential energy diagrams really show how the potential energy of molecules change. Remember that the potential energy is the energy stored within the bonds. So when you break a bond, you have to apply that amount of potential energy. When you form a bond, you release that amount of potential energy. And so potential energy diagrams allow you to take a look at that. So you can see that we've got potential energy on the y-axis. We've just got the reaction coordinates on the x-axis. So reactants to products you should recognize. There's going to be a lot of other things that we can use to the potential energy diagrams to identify. So I'm actually going to start with a blank one. You've got the ones that already show things labeled and so forth, so there's a little less work that you have to do because you can label the one that's already there. So we're going to start off with a potential energy diagram for an exothermic reaction. So I'm just going to very quickly give myself some axes here, and potential energy diagrams don't necessarily have to be proportional as far as the axes go. We just are going to label the important parts along the y-axis. So the one thing that you are going to recognize in a potential energy diagram that is exothermic is you always start the reactants high and you always end low with the products. So here's the reactants, here's the products. We have to talk about what's going on inside this center area, but that's where we're starting. Okay, so what you already know, let's say that this value is 70 kilojoules, and let's say that this value is 20 kilojoules. Okay, and this last value up here we'll say is 100 kilojoules. Again, things don't have to be proportional. We just are going to label the important temperatures on the potential energies on the y-axis. All right, so reactants possess this much internal energy, 70 kilojoules, let's say. These numbers are going to be really low. If you remember the bond energy stuff, they were in the hundreds, but for us, it's easy to just keep numbers low. So reactants are going to have more potential energy than products in an exothermic process, because as you go from reactants to products, you have to give off energy. Well, the difference between the reactants and products is what you have learned to call the delta H. And so in this case, to get from the reactants to the products, we have to give off this amount of energy. That's how we know it's exothermic. So an exothermic reaction for the potential energy diagrams shows a drop in energy with the products. Products possess less energy. More energy is given off when they are formed. So some of the other things now. This center area represents the arrow, essentially. So what's happening? Well, in order to get any reaction to start, remember that we have to apply some energy. We have to apply the activation energy. The activation energy is the energy needed to get from the reactants up to this big hump. This is kind of like the threshold energy. That's the energy you need to start the reaction. And this is called the activation energy. The energy that you have to add is called the activation energy. So in this case, the activation energy is 70 up to 100. So the activation energy in this case is 30 kilojoules. The delta H, by the way, was a negative 50 kilojoules because we lost that much energy. So that's the basic idea of a potential energy diagram. It is showing you the bonding schemes that take place. Now, this activation energy is actually creating a new kind of bond. If you think about the one reaction that we talked about in class when we were looking at the molecular collision theory, I said the H2 plus I2 yields 2HI bond we were talking about, remember? And we said very simply, if this could happen in one step, it would have to happen something like this. We would have to break those bonds. We would have to form these bonds. and you create, if something doesn't happen simultaneously, you create what's referred to as an activated complex. So that's what this point up here represents. The 100 kilojoules represents something called the activated complex. The activated complex is that intermediate structure. It's not stable. So as we're forming the new bonds and breaking the old bonds, you have a intermediate structure. You have a molecule that is not stable, because you know hydrogen shouldn't have two bonds, yet it has this one and it has this one if everything hasn't completed itself yet. So the activated complex is an unstable intermediate structure. It kind of resembles the reactants, it kind of resembles the products, but it's still not quite there. And because it's not stable, it has a huge amount of energy associated with it. So for any chemical reaction, you have to apply the activation energy in order to create this activated complex. Once this activated complex is created, now you can continue moving forward to create the products, finish breaking the old bonds, finish forming the new bonds, and then you wind up with that structure of the products that you wanted. So you start off with the reactants. I guess that's not a very good shape or size equivalent. You start off with the reactants, you create this activated complex, and then you wind up with the product. So those are the 3 points on the potential energy diagram. Now there's one other important thing to remember in terms of a potential energy diagram. You could have the energy go backwards. So once you create this activated complex, there's no reason that this activated complex can't roll back down this side of the hill so that you would have an ineffective reaction. So reactions can go, some reactions can actually go both ways. Even once you get to the products, there's nothing that says these two couldn't collide once again and go backwards to create the reactants that you started with. So you can have reverse reactions as well. And that's something that you're going to see more of as we move into Unit 10 and 11. So a reverse reaction would be really going from products to reactants. So we show that any reaction that can be reversible, we show with a double arrow because it means it can go both ways. So now let's take a look at what would happen with the potential energy diagram. Potential energy diagram would be showing a delta H from the start point to the end point. Even though these used to be called the products, now technically the reactants if we're going in the reverse, but the right side versus the left side. Our delta H in reverse hasn't changed except for one thing. Can you think of what that is? The sign. So the delta H in reverse would actually be a positive 50 kilojoules. In order to get from the products to the reactants in the reverse, we would have to apply a sum total of 50 kilojoules of energy overall. The other big thing that changes, and I'm running out of space on this graph, the other big thing that changes is the activation energy. Because now we have to get up this side of the hill. Whereas this one was pretty easy, this one is much harder. So the activation energy in reverse is actually going all the way from the reactants. And if you can put this somewhere different on your diagram, feel free to do that. I feel like this is the only clean place I have. So energy of activation in reverse is now from the products up to the activated complex. So you look at this, and it's an actual 80 kilojoules. By the way, activation energies are always positive. You always have to apply that quantity of energy. Delta H can be positive or negative depending upon whether it's exo or endothermic. So if you take a look then at an endothermic reaction, which will help us be a little cleaner here. So for an endothermic reaction, we're going to start low and end high, because in an endothermic reaction you have to overall apply energy. So our delta H for an endothermic reaction is going to be some sort of positive value. So let's put some numbers in there. Let's say 30, 80, and 60. Okay, so that means it's a positive 30 kilojoules for our delta H. In the forward, our activation energy is pretty big. That's why it's an endothermic reaction. You have to overall put energy in to get the reaction to work. So the energy of activation in the forward is 50 kilojoules. In the reverse, the activation energy is only 20 kilojoules. Sorry, text message coming in. Activation energy in the reverse, or I'm sorry, the enthalpy in reverse. Again, no difference in value, just a difference in sign. So to go from here to here, we're losing energy. To go from here to here, we're gaining energy. So those are probably the big things about potential energy diagrams that you got to be aware. We're going to practice a little bit. But, one more thing. Catalysts. Catalysts are going to, sorry, let me move this paper up some. Catalysts are going to give you an alternative path, and what they really do is they decrease the activation energy. So by offering you an alternative route, a catalyst is going to do something like this, where it lowers your activation energy down to, let's say that's 70 kilojoules. So with a catalyst, and you always show the catalyst as a prime usually, so the forward in the catalyst, if the catalyst is at 70, so now the activation energy is equal to just 40 kilojoules. So a catalyst doesn't change where the products are, doesn't change where the reactants are, but it lowers the activation energy by giving you an alternative activated complex. So for example, with this guy up here that we've been talking about, if I put a catalyst in, maybe it's not this structure that I'm creating. It's something alternative, and I know you're thinking, how can it be something different? That's really the way it needs to collide. Well, remember, most reactions are not that simple. So a catalyst really would offer an alternative arrangement for the activated complex. All right, so let's practice a little bit. We've got only a few minutes of video, and I'd rather not have to do a second one. So if you have something like this, where the activation energy, let's say it looks like this, okay? And so you've got, this is at 80, this is at 110, and this is at 50. Can you give me these values? Energy of activation, reverse. Okay, so pause this here and try and solve those problems. All right, so if you've paused it and given it a shot, you will see that the activation energy the delta H in the forward is going to be 80 down to 50. So that's a minus 30. In the reverse, it's the same value but opposite sign, plus 30. And these are all kilojoules. If we have activation energy from 80 up to 110 is a positive 30, but in the reverse, it's 50 up to 110, so it's a positive 60. So there you have that one. Okay, one more. So if I tell you that the reactants are starting at 20 kilojoules and the delta H is a positive 40 kilojoules, and the energy of activation in reverse, let's do the reverse. Energy of activation in reverse is a positive 30 kilojoules. Take a moment and draw that potential energy diagram. So again, pause it, draw it, and then compare to what I've got. Okay, so you've paused it. So reactants, I'm starting at 20. Since delta H is a positive, I know that my products are going to be higher, so I can start my 20 down here. Since delta H is a positive 40, that means that my products must be at 60. So my products are going to be over here. My reactants are going to be over here. Activation energy in reverse is from where my products to the activated complex is. So plus 60, or 60 plus 30 gives me 90. So there's my potential energy diagram. Delta H in forward is 40. Energy of activation in forward winds up being plus 70. Delta H in reverse is minus 40 because I'm stepping down, so this winds up being an endothermic reaction. If we were to add a catalyst, and the catalyst lowers the activation energy by 10 kilojoules, what would you do with it? Well, instead of having a peak up at 90, you'd have it at 80. So there is where your activation energy would be with the catalyst. Finish that word. Okay, so pretty much out of time. So you've got a bunch of problem sets to do to practice all this. So think if you're given positives or negatives and forwards or reverses. But otherwise, that's a pretty straightforward idea. All right, good luck.